Good afternoon, good morning. This is USF Transition Seminar on Fridays, and welcome to this seminar and thank you for being here. This seminar is sponsored by the Department of Civil and Environmental Engineering at USF, as well as the Center for Urban Transition Research. And it also co-sponsored by three UTCs at USF. One is National Institute for Congestion Reduction, US DOT National UTC, and also CTEC, Center for Transition Environment and Community Health, at Tier 1 UTC, and also TOMNET, the Center for Teaching Older Models New Tricks, at Tier 1 UTC as well. And it's also facilitated by ITE Student Chapter at USF. So today we have honorary speaker from the West Coast, and actually he's the dissertation advisor of Dr. Qing Liu, who's associate professor in our department. So I will invite Dr. Qing Liu to introduce our guest speaker today.
Thank you, Dr. Well, it is a great pleasure for me to have Dr. John Harvey, my former advisor and mentor during my study and work at the University of California at the Pavement Research Center at both Davis and in Berkeley. And during my study and the work period in California, Dr. John Harvey gave me tremendous support, mentorship, and guidance and training, and which shaped my career path and my fields of expertise in pavement engineering. So let me give a brief introduction about Dr. Harvey. Dr. Harvey is a professor in civil and environmental engineering at the University of California at Davis. He's also a director of the University of California Pavement Research Center and a director of the City and County Pavement Improvement Center. He's a past chair of the Transportation Technology and Policy Graduate Group, and he's also a principal investigator for projects for research, development, and implementation for a wide range of pavement materials, design, asset management, cost, and environmental topics for the California Department of Transportation, known as Caltrans, Federal Highway Administration, FAA, Care Recycle, the California Air Resources Board, and the Transportation Research Board, and other state DOTs and industry. He has previously been a researcher and the adjunct professor at the UC Berkeley, and also worked in pavement consulting companies in Nigeria and Texas. He has a bachelor degree from Oregon State University and a Master of Science and a PhD degree from UC Berkeley. And he is the founder of the International Symposium for Life Cycle Assessment of Pavements. He's also a professional civil engineer, licensed civil engineer in California. So please join me in welcoming Dr. John Harvey for his talk.
Thank you, Jing. Thank you. Can you hear me?
Yes.
Video sound good? Okay, let me check the screen. And can you see the screen well?
Yes.
Yes.
Okay. Thank you very much, and thank you for the opportunity to speak with you today. Greatly appreciated. I'm going to talk today about advancing the sustainability of pavements, and particularly about methods of quantification and their application. So I'll talk a little bit about sustainability concerns, and those vary around the country and around the world. I'll be giving a kind of a California perspective on a lot of things, but then talking about how that can relate to the situation in different places. I'll be talking about the pavement life cycle and some of the primary ways that right now we can see ways to reduce impacts. I'll then introduce life cycle assessment in sustainability analysis, kind of walk through it, and some applications and some example case studies, and then an approach for prioritizing what we want to do called supply curves. And then I'll briefly introduce a new area that's growing, which is called social life cycle assessment, and then some conclusions. So some of the motivations to improve the environmental performance of pavement. First of all, pavement uses finite resources, which is important. We need to make finite resources last for future generations. Pavement produces pollution, and pavement affects quality of life. And I won't get in today into the idea of multifunctional pavement, meaning you know, all the different ways that pavement affects our life. We normally think of pavement as something that trucks drive on and cars drive on. But if we think about it, 20 to 40% of the surface area of cities in the United States is pavement. So up to 40%, and that has a tremendous effect on flood control, stormwater quality, our ability to move around by means other than vehicles, walking, bicycling. It affects the thermal environment in the city. So pavement is there. Most people don't want to think about pavement, and most people, to be honest, only think about pavement when it's bad. Not many people, you know, get home at night and think, man, I really used some really good pavements today. Really happy for those pavements. So, so they're there and they're important. So now we can make significant contributions to reduce these impacts. There are political forces that are pushing this, and at the local level, nobody wants to live in a high pollution environment, and nobody wants to suffer the effects of climate change. And at a global level, there's an awareness of the global mechanisms and the way that we're changing the environment that affect human society. Now, this translates more and more into market forces. Industry feels increasing pressure from the public as well as from government, and a desire to compete in terms of environmental impact as well as cost. Our pavement industries have always competed, and companies have always competed on cost. Now they understand, and they're competing in terms of the environment. And I'm going to talk about quantification a lot today. And the key here is, and what motivated us to get into this, is to move away from green marketing and get to actual quantifiable performance measures, and then checking how are we doing in terms of meeting those performance measures with regard to environmental impact. Government pavements must remain, well, they're not necessarily financially sustainable right now, but you know, government should not go bankrupt trying to maintain pavements. Now, one of the great things about what we're going to be talking about as we start quantifying is that we find that environmental improvement often also leads to reduced life cycle cost. So how do we advance towards sustainability? 20 years ago, people said, well, I'm recycling, therefore I am sustainable. As you'll see in a document that I'll point to pretty soon, I don't believe pavements are sustainable at this point. We need to be moving towards more sustainable pavement. And people sometimes just focused on global warming potential, and that's not the total story in terms of environmental sustainability either. I'll walk through some other measures and contextual concerns about that. So I believe, and I'll keep emphasizing this, that the good answers are going to come from full system analysis and complete life cycle based decision support. Full system means that we consider all the resources, processes involved in the pavement life cycle and the context of the structure, traffic, climate, and soil. And we need to look not just at global warming potential or how much recycling we're doing, but look at all the environmental and resource use impacts of interest for the local decision-making authorities. And we need to look at interactions and effects on other systems. In terms of complete life cycle, that means that we look at the consequences of our current decisions as far into the future as we can with some certainty. In California, at the state level, we've switched from 20-year design lives for our major rehabilitations to 40-year design lives, which means that we're really not doing a major rehabilitation or reconstruction until about 60 to 80 years. So that's an idea of the time framework that we're looking at for some of our longest lived pavements, up to 80 years. Gets less certain as we get out there, something to consider. But pavements are they're not as long-lived as bridges and dams and some buildings, but they are long-lived assets that we need to consider that full life cycle. And we need to look at the effects of our current decision on how much flexibility they give us to make future decisions. Now, the bottom line I would advocate is that we need to set sustainability goals, performance measures, performance goals, and then routinely use quantitative approaches in our work to address and work towards those goals. I'm going to give you some California context here. This is the years on the bottom, on the x-axis. This is annual greenhouse gas emissions in millions of metric tons of CO2 equivalent on the y-axis. This is data as of 2015. The blue line is California's emissions. So we're at about 430 million metric tons back here in 1990. That's our benchmark, is 1990. The governor, Arnold Schwarzenegger, signed AB 32, Assembly Bill 32 in 2006, that set goals for 2020 and 2030 for greenhouse gas emissions. The yellow, so this is how we've done since that law was passed. The yellow line is our business as usual reference scenario. And here's our first target. We've beaten that. That is to get back to 1990 by 2020. We're looking down here at about a 50% reduction in 2030, a little less than 50%. And if we do business as usual, we're not going to make it. The regulatory goal, this wasn't law, the regulatory goal by 2050 was to get back to about less of about 90 million metric tons by 2050. This has been updated with new regulations which aim for us to be carbon neutral now by 2045. And all of our industries, pavement industries, have now produced plans to get to net zero by 2050 or 2045. The last part of these are going to require sequestration strategies of some sort. The main three strategies that the Air Resources Board has focused on, and the Air Resources Board is our lead agency on climate change, has focused on land use planning to reduce vehicle travel, to convert the fleet to natural gas and then electric and fuel cells, and to reduce vehicle miles traveled. These get us some part of the way towards these goals, but really my question, and I think this is the question for every other sector of the economy, is what's our role? Because these three strategies are not going to get us there to these targets. Every sector of the economy in California has actually got to make changes to get there. So these are our emissions in 2017. They're pretty similar to the last complete inventory, which is 2019. You can see our electricity sector is down quite a bit. We still import, in peak times, we import electricity from coal burning states up here. Our residential's getting down there. Our industry's getting down there. Our big dog here is transportation. That's 40% of our emissions in California, 28% passenger vehicles, 8% heavy duty vehicles. The red boxes I've put here are the parts of this total economy emissions report that involve the pavement industry. So we use cement, which is 1.8% of our emissions. We produce about 80 to 100%, depending on the year, of our cement in California and Nevada. Our oil and gas extraction, we are the third to fifth largest. I think we're now the fifth largest state in terms of oil extraction, oil and gas extraction, and we use some of that oil to make asphalt. Our oil refineries are 7%, and that's where we take the crude oil, and the first product that comes out of that is the heavy bottoms, which is asphalt, which we use to make roads. I've circled the vehicles here because pavement has an influence on the energy and fuel consumption of both heavy-duty vehicles and passenger vehicles. The rougher the pavement is, the more fuel that's consumed. the more viscoelastic the material is, the more viscous, the more energy that's consumed, and also through the surface texture. An overall look at this is that this is my back of the envelope estimate that of our approximately, let's call it 450 million metric tons per year at our baseline, keeping pavement smooth and optimizing rolling resistance, I think we can, our estimates are we can reduce about 1.5 to 3 million metric tons, reduce cement use by 50% in pavement, we get this much, reduce virgin asphalt use, we get this much, and just make pavements last longer and reduce the amount of hauling in terms of demolition and hauling out, and oil and stone and cement hauling in. Here we are. So this gets us to about 3 to 4.5 million metric tons of reduction in the pavement sector. That's about 1% of the, a little less than 1% of the total state total. And some people might say, well, why should we even worry about that? Well, the reason is because, you know, pavement and 50 other industries, sectors of the economy, if we all make our 0.5 to 1% change, that's what it's going to take for us to hit our reduction in global warming potential goals. And this is up to about 3.5% of our big one here, which is transportation. So we're not the biggest ones. We're amongst the middle ones. Every sector of the economy is going to have to make its contribution if we're going to hit our goals. Now, global warming is not the only thing. This is smog, ozone non-attainment 2015. And guess where all the extreme and severe ozone pollution, ground level ozone pollution, it's primarily California. Big reason is we emit here in the Bay Area and Los Angeles, and we have 12,000 foot mountains holding all of that in the Los Angeles basin, and we have the Sierra Nevada here holding that in the South Central Valley. Now, unfortunately, also, these areas are also amongst areas where we have some of our most disadvantaged neighborhoods, and the air pollution tends to be worse where the incomes are lowest. I'll talk about that when I come back to social LCA. This is PM 2.5 non-attainment, again, the San Joaquin Valley and the Los Angeles Basin. And this little area down here, right around the Port of Los Angeles and the Port of Long Beach, which are the #2 and #3 cargo ports in the United States. This is where most of our trade with Asia comes through these two ports right here, and lots of trucks and trains here. And this is an area where about 35% of the children have asthma, and a lot of that is driven by PM 2.5. So my point here is, in addition to global warming, we have some major other environmental impacts that we need to care about. Now, if you're in a different part of the country, you may have some other types of impacts. And this is kind of the contextual part when I get to life cycle assessment of setting your goals. Do we have to take ourselves to the poorhouse to achieve these goals? And this is again from the Air Resources Board. Our goal is to continue to grow our economy and grow our jobs while reducing emissions. As I mentioned, reduced greenhouse gas correlates and moves. If we're burning less fuel and refining less and extracting less oil, we're reducing the amount of PM 2.5 and smog. But this is how our GDP has grown in California since 2019. This is how our population has grown since 2019. These are percent changes since 2000. This is how our greenhouse gas emissions have gone, and then per capita, and then per GDP. Now, we really want to continue this trend, but to be honest, we've done a lot of the easy things, and now we need to start getting to the harder things to hit those steeper goals that we need to hit. But this is our goal, is to keep these, good economic, although we have a lot of inequity that we have to deal with, and keep these going. I want to point folks towards the Federal Highway Sustainable Pavements reference document. And you'll notice that this is called Towards Sustainable Pavement Systems. This is being clear and frank that we don't really know how to really have completely sustainable pavement systems yet. We need to keep moving towards that goal. This covers beginning to end of the pavement life cycle, complete system as we knew it in 2015. It's written in a life cycle. The chapters are through the life cycle, and it summarizes strategies, some of which I'm going to talk about today. And that's a free download from the Federal Highways website. So thinking in terms of the pavement life cycle, I'm sorry, in terms of any product's life cycle, we have stages through the life cycle from left to right. Normally, most of the time, unless this is just a pure human service, we have raw material acquisition. And raw material acquisition, as well as the other stages, require materials and energy input. And often those are finite resources, which we want to track. And then as a part of producing the product, we produce waste and we produce pollution, which we want to track. These are called flows. These are the input flows. These are the emission flows. And then as we move from stage to stage, we often have transport in between the different stages. So here we have materials acquisition, processing, manufacturing, use, and end of life. And then we have arrows going back through reuse, remanufacture, and recycling outside our own process stream. We also have recycling into our process stream from other process streams as well. So this is the basic life cycle. And each of these outputs in terms of waste and pollution can be translated into environmental impacts and life cycle assessment. If we now look at that in terms of the pavement life cycle, we have materials acquisition and production, extraction of oil, refining of oil, extraction of limestone and other minerals, processing of cement, mining of aggregate, and so on, a lot of other products. We have design decisions. We have construction and maintenance, which involves equipment use, transport, traffic delay. We have the use stage, and the biggest one here, typically, the two biggest are pavement performance. How long do we make these materials last so that we don't have to do the materials and construction as frequently? Primarily driven by construction quality control as well as design. We have the rolling resistance, which is the impact of the pavement on the vehicle energy use. And as I mentioned, pavement has other multifunctionalities such as stormwater control, lighting, and so on. And then we have end of life. The truth is that pavements almost never die. They get recycled back. 70 to 99% of pavement materials get recycled back into pavement, depending on the state. So what are our tools for quantifying? We use life cycle cost analysis to calculate costs over the life cycle, and we use life cycle assessment to look at environmental impacts, energy use, and finite resource depletion. And increasingly, we're starting to look at social LCA to consider jobs, accessibility, and the equity of the impacts and benefits of pavement. So where can we reduce pavement impacts? We can reduce them throughout the life cycle: design, materials, construction, operations. If anybody wants to sing the Circle of Life here, go ahead, break out here from the Lion King. So we can work in construction, and construction is often our biggest variable. If we get good construction quality control, we can double the life of the materials that we've placed. And if we get bad construction quality control, we can have that life. And many state DOTs, Florida DOT is out there in front in leadership on construction quality control. But we need to remember that in many cases, in California, 50% of the pavement materials used every year are used by local government, who often don't have those kind of more sophisticated quality control systems. So we need to think about local government in this as well. Local government owns 80% of our lane miles. They spend about 40 to 50% of our pavement dollars. Compaction of asphalt and smoothness of concrete and asphalt are amongst our most important properties that we get out of construction. We need to measure the quality. We need to enforce the specifications. We need to look at our specifications and find ways that we can balance risk and allow the use of lower impact materials with some where we have some 80% assurance that we'll get the same or better life. We can't let the perfect be the enemy of the good, but we can't do stupid things either and just open up our specifications to everything. Design, we need to find ways and look at structures to use less material to get the same life, or use less impactful materials to get the same life. And then preservation treatments, things we do on the surface of the pavement can help us extend the life of our materials with small impacts. So where do we focus? This is a life cycle of a pavement. Here we have years on the x-axis. We have the initial treatment. We have a maintenance treatment. We have a rehabilitation treatment, future maintenance, future rehabilitation. Use of our pavement management system to optimize the timing of these is very important. So asset management is a major area where we can bring in life cycle assessment type goals. We've implemented global warming potential into the Caltrans. Caltrans has implemented it into their pavement management system, and that allows them to do their 40-year look ahead of maintenance and rehabilitation for the entire state network, and also calculate and look at things they can do, such as optimizing smoothness in terms of triggering treatment to minimize air pollution and greenhouse gas. So each time that we do a treatment, we get an orange arrow, we get a bump in emissions from materials and construction and transportation of materials and demolition. In between, we have increasing roughness, and we have an increasing amount of interaction of the pavement with the vehicles, smoothness, viscoelasticity, and macro texture. And as the macro texture and smoothness get worse, we have increasing rates of environmental impact. So what we're trying to do in asset management and to some degree in design is balance the amount of maintenance and rehab we do with the benefits of doing it, which gives us smoothness. So figuring out the optimal timing is a major thing we can do. On our lower traffic volume routes where there's not that many vehicles using it, we really want to focus on the materials, the transportation, and the construction. On our higher traffic routes where we have lots of vehicles interacting with that smoothness, that rolling resistance, we want to focus on minimizing that rolling resistance, primarily roughness, but also structural response of the asphalt and the macro texture. For all pavement, we want to make the same material last longer through good construction quality so that we don't have to do so much maintenance and rehabilitation, and we extend that life with good construction quality and with preservation. And for high traffic and construction, we particularly want to get, we want pavements to be, a pavement that's born rough only gets rougher. So getting good initial construction smoothness is very important, and especially for those high traffic routes. I'm going to walk through an example or two for each stage of the life cycle. We'll start with materials. California and Florida is also what we call a rubber state, a tire rubber recycling state. So this is a comparison we did about 10 years ago, and we found through research that this is my metric version, about 2¼ inches of rubberized gap graded, 2¼ inches gives us the same reflective cracking life as a thin overlay as 3 inches of hot mix asphalt with 15% wrap. Now, this rubberized mix has more virgin binder, and virgin binder is about 40% of the global warming potential of an asphalt mix. So it has more binder, it's more impactful per ton, but because we can use less of it to get the same performance, we actually have a benefit in terms of global warming potential, these two giving us the same performance life of about 5 to 10 years, depending on the traffic. And over here in an asphalt material, you can see where the impacts are in an asphalt material. A small amount is the aggregate production. The asphalt binder production, which is the extraction and refining of the oil, is the green part. the transport of the materials, and typically transport for any materials 5 to 15%. The other big one for asphalt is the amount that we have of heating, natural gas that we use in the asphalt plant to heat the binder and the aggregate so that we can mix it. So the main sources in asphalt are binder production and heating. Wherever we can find ways to reduce those, replace some of the binder with recycled binder, find ways to use warm mix and half warm mixes to reduce the heating. That's where we address the bigger issues. And this is an example of, if we can quantify these things, we can focus, use Pareto principle and focus on the biggest sources of emissions as our first focus. Florida is a big user of SBS polymer, actually a big pioneer in the use of SBS polymer in your surface mixes. A lot of research by Florida DOT with the heavy vehicle simulator. Now, we know that SBS, if we add 3% SBS polymer, we increase the global warming potential of that mix by 18%. This is a very intensive additive. And this results come from the Asphalt Institute life cycle assessment. Now, the question is, so this means we shouldn't use SBS? Well, no. If we can get more than an 18% increase in life, which Florida DOT has demonstrated that they can compared to a conventional mix, then we actually have a net reduction in global warming potential and air pollution. So this is a case, this is a reason why we don't want to just look at the initial impact. We want to look at the full system and the full life cycle. With regard to recycled asphalt pavement, again, nationally, about 90% of asphalt is recycled back into new asphalt. We're trying to push the amount of RAP that we use from 15%. California, we're trying to get to 40% in the next couple of years. But when we go higher, we have to add what are called rejuvenating agents to get that old hard binder to soften and blend. And we have three choices for that: petroleum distillates, which are very impactful, and a couple bio-based non-food vegetable oils and tall oils from pine trees. We're trying to work with these industries to get an idea of these, but again, full system, we get a reduction in impact from using the RAP, but we need to also account for the impacts, the increased impacts from the rejuvenating agents. Turning over to concrete, cement is an incredibly, Portland cement, hydraulic cement is an incredibly carbon intensive process. I don't know if folks know where cement comes from, but it comes from mining limestone and aluminum ore and some iron ore, and then burning them, and burning those rocks so hot at very intense temperatures, which is very energy intensive and carbon intensive. And that energy, that temperature is used to drive the CO2 out of the calcium carbonate. And that's how cement is actually produced. So it's a double hit in carbon because of the energy as well as the CO2 coming out of the rocks. So a cement industry under intense pressure to reduce that. And some of the paths are to reduce the amount of cement through better aggregate gradations. California is a little late on this, but increasing the amount of ground limestone. And we found this actually gives us, again, better performance as well as reduced emissions. Portland limestone cement. Other supplementary cementitious materials, some of these that we're looking at are cellulose, nanofibers, and nanocrystals. And these come from trees. And again, trying to reduce our fuel load in our forests. Changes in design specs. One of the things that we found is a lot of local agencies have never reviewed their concrete specifications, and they're requiring things. It's using technology and concepts from 20, 30 years ago. An example in California was we went and looked at some concrete mixes from a city, and we looked at their urban street requirements and the mix designs they were getting, and they had this amount of CO2 per kilo of Portland cement concrete. Their playground mixes had this amount because they were not replacing cement with supplementary cementitious materials. We went out and looked at a typical mix, a mile away on the state highway carrying heavy vehicles, and they were using supplementary cementitious materials, and the state highway mix had this carbon intensity. And because the local government hadn't looked at their concrete specs and they were requiring minimum cement contents, they were far more carbon intensive. And in fact, that extra cement was hurting them because they're at greater risk of drying shrinkage cracking. So they were getting worse performance, more cost, and greater environmental impact. So I won't walk through all of these. I'll just give an idea of some of the construction. Now moving from materials to construction and transportation. In construction and transportation, there's a lot of the way that we put the work together. In heavy traffic areas, the construction work zone traffic handling can increase emissions. We're modeling that and bringing that into our life cycle assessment now. The equipment that's used in construction, and I'm expecting that within 15 years, we're going to have requirements in California that most of our construction equipment switches from diesel to electric. And as I mentioned, construction delay. Construction quality. This is usually our biggest impact, not some magic bullet material or miracle carbon sequestration. Construction quality, the nuts and bolts, bread and butter, day-to-day nitty-gritty of construction quality is our most impactful place that we can make changes in pavement. That means good compaction and making it smoother, and good mix designs and delivering the material that was specified. That requires less frequent treatments, less frequent construction, less pavement vehicle interaction, and fewer social impacts. The public somehow doesn't like, every 3 years we're back out there with a construction work zone delay because our materials didn't last as long as we planned. Hauling is a big issue, and our mode of transportation of hauling. Hauling by truck is about 5 to 8 times more impactful than maritime, and about the double of rail. So some other ways we can reduce this is using in-place and side-of-the-road cold central plant recycling, so that we're not hauling materials in and out. We're recycling them in the construction work zone, and thinner designs for the same design life, reduce the amount of hauling. Looking at the use stage now, 3 main areas of rolling resistance. And is this important? Well, rolling resistance can change the fuel use in an internal combustion engine by 0 to 8%. This 0 would be our baseline is a very smooth pavement. No structural interaction, no viscoelastic energy loss, and a macro texture that's sufficient for skid resistant, but is not excessive macro texture. And 8% of every vehicle rolling down the road, 1%, 2% of every vehicle rolling down the road on a high volume road is more carbon than all of the materials and all the transportation and all the construction rolled up together. So this is a big deal, particularly on high volume routes. So roughness is, we measure in terms of International Roughness Index. And basically what's happening is the vehicle is dissipating energy from the roughness through the shock absorbers and the tire sidewalls. It's converting mechanical energy into heat and then dissipating it out into the air. That affects all vehicles all the time. Structural interaction dissipates energy through a viscoelastic time delay effect or delayed elasticity, and asphalt is a viscoelastic material. So this can affect up to about 4%. Appropriately looking at the stiffnesses of our materials in our pavements can help us with this. Now, this is not that big a deal for light vehicles. This is not all vehicles all the time. This is primarily heavy vehicles moving slowly in warm temperatures. Macro texture is the surface texture of the pavement, and that dissipates energy through tire tread distortion. Typically not as important as either of these. How important is this? This is International Roughness Index. Here's a 1 meter per kilometer or 60 inches per mile, and that's our baseline. You can see some of the impact on cars, not that much. The different lines are for different traffic speeds, car speeds. Our current federal trigger baseline for triggering going from a good pavement to a fair pavement is about a 3. And you can see at 3, we're typically increasing the vehicle fuel use and the carbon emissions, therefore, by about 5% for every car. Over here for trucks, much more sensitive to speed, and actually the impact is worse at slower speeds than at higher speeds. And again, when we're at that federal trigger, we're anywhere from about 2% up to about a 5% increase in the emissions, the fuel use and the emissions from trucks. And moving from use stage to end of life, this is where the recycling is the big deal. We can use our materials back into the same materials. That's the highest use, replaces virgin materials. We can downgrade it to a less important material. We can send it to use it as fill. We can send it to the landfill. These are not good choices here. This is the best choice. Now, nearly all existing pavement materials are perpetually recyclable in one form or another. And we can do that at the plant, or we can do it as shown in this photo. This is where we're taking an existing asphalt pavement that's badly cracked and grinding it up in place and injecting foamed asphalt and cement into it. And then we'll compact it, and then we'll put a thin rubberized layer over the surface. And we've hauled in 95% less material than we would if we've removed and replaced this. Lots of folks talk a lot of the time about recycling other waste streams into paving materials. This is when I get media inquiries, this is about 50% of them. Sometimes these are somewhat viable. Sometimes it's just kind of, well, it's just pavement. Why don't we just recycle the garbage into the pavement? I would recommend not doing that without some really good care and life cycle cost analysis and life cycle assessment to see, is this really a good thing? Are we the 4 questions that we ask are, do we get the same performance or better? Do we get the same environmental impact or better? Do we get the same life cycle cost or better? And do we allow future recycling? Or if we recycle this material into our pavement, does that mean that we can't recycle it in the future because when we run it through the mixing plant, we're going to produce toxic fumes or something else, or it just won't work technically? So if we can't answer these 4 questions positively, then it's, or at least with the 80–90% assurance that they'll be positive, then this is probably not a good idea. Okay, so some of the initial takeaways, I have a little bit more stuff after this. For pavement, we can make contributions to improve the environment. Pavement has a very complex life cycle, many system interactions, many alternatives, and many trade-offs. All of us in the pavement enterprise need to innovate. Engineers, asset managers, planners, many parts throughout the life cycle where we can innovate. We need to do the benefits assessment to avoid negative unintended consequences. And it's not just materials. Most of the focus in the public and in the media is on materials, but our biggest impacts, most beneficial impacts, will come through design, construction, and pavement management changes. We need to quantify these things. Again, I'm going to emphasize that we can really screw it up if we don't quantify and do some due diligence with our life cycle assessment and life cycle cost analysis and look at the full system and complete life cycle. And thinking about life cycle will lead us to better ideas and more ideas. The system to quantify these alternatives and for the full system and complete life cycle, I'm going to advocate for is environmental life cycle assessment. Why? Because it's quantification. It has its issues, but it's the best approach I think we've got right now. It does consider the full life cycle, and it does consider everything within the system boundary, including important interactions and potential unintended consequences. And we actually have two types of LCA. We have attributional LCA, which considers that the market will not change. We're just gonna alter the processes in the market. And then we also have consequential LCA, where basically we're going to bring in an innovation that's going to completely change the market, and the processes are not going to be the same. We're going to have actually different processes. There's a number of LCA standards out there. Pavement LCA should follow these ISO standards. These are not regulations. There's no agency that regulates these. These are voluntary. These only provide general guidance for all products, not detailed for something like pavement. And I want to note that these are not carbon footprints. Carbon footprints typically only considered the initial impacts, and I really want to advocate that do not just consider the initial impacts. We need the full life cycle. This is another document I'll point to, and here's a live link in the presentation, which I've sent over for posting. And this is 2016 guidance on taking those generic ISO requirements and applying those to pavement. For those of you who aren't familiar with life cycle assessment, the 5 steps are goal definition and scope. This is where we define the questions that we want to answer, and these should be tied to our local sustainability goals. And then we define the system that we're going to analyze. Once we've got that, we then do what I call the accounting stage, which is where we develop the quantitative flows of energy and materials into the process and waste and pollution out of the process per unit of product that we actually want to produce. So this is where we do the flows. We inventory the flows. We then have equations and models that convert those flows into impacts like global warming potential, like ozone potential, like PM 2.5 production. This is our impacts. We then interpret those impacts, basically looking at those impacts and what do they tell us? How do we use those to answer the questions that we posed back up here in our goal statement? And then a critical part also is outside critical review. LCA really only stands up if people have some faith in it, and faith in the results requires transparency and an outside critical review by all the stakeholders. Basic unit process in LCA, just a few details of LCA. Every step through a pavement's life, we have what's called a unit process, and we track the resources and energy in per unit of product produced and the waste and emissions that come out. Some example unit processes and some defined units would be, we could model this for 1 ton of asphalt, or 1 ton of concrete, 1 yard of concrete, or 10 lane kilometers of concrete, or 1,000 square meters of asphalt concrete, and so on. So this is done for each of our processes. As we move through the processes of, say, producing aggregate, and then the aggregate goes into the asphalt concrete, we do what's called balancing, so that the quantities are matched up to the proportional quantities of materials used to produce the final product. And then what's proportioning there is then the upstream materials extraction, the amount of electricity, fuel, etc. So balancing means scaling the input and output to the functional unit. And this is basically, when we do this for the full system, this is giving us our LCA model. This is an example of a model for the initial construction of a full depth recycling of an asphalt pavement with cement. And we can see materials extraction, aggregate, asphalt binder, mixing those, hauling them to the construction site, creating the cement that also goes into the mix, hauling that to the construction site, construction use, and that's a model of that treatment. So that's the inventory. We convert those into impacts. The flows get converted into impacts. We have primarily used in the United States the Tracy system from the US EPA. In Europe, they use the CML system. These are different. I primarily point to the Tracy system in the US. So these are the impact categories that come out of typical LCA, different kinds of energy use, resource use, emissions, climate change, ozone layer depletion, and so on, toxicity, freshwater use, and hazardous and non-hazardous waste. These are the ones that are most important in California. These are the ones that give us the most problems. But this should be context specific. What are the most important in Florida? Probably somewhat different. And then the other thing we're starting to look at is the equity of who's exposed to. Everybody's exposed to climate change, but who ozone and toxicity are local. So who gets exposed to those is part of our social LCA. To put together a tool to do LCA, this is another document I'll point to. I'll point back to the life cycle assessment framework. We need to define the system. We need to and the processes. We need to define the data to support the models. We need to collect the data for the models. We need to organize it and validate the data, put the models together, produce a tool, and then we can go and do project level assessment, specifications, and policy. Making great strides in this, and we're here now in the United States, and there's a couple tools that are out there. Chicago Toolway tool was an early one. One that we're just rolling out in Caltrans right now is called Lcap. It's a web-based tool, and web-based software currently being implemented by Caltrans. And I also want to point to another tool which we helped put together for the Federal Highway Administration, free download spreadsheet tool with national inventories called LCA Pave. Got a couple minutes here. I'll give you just a couple examples of these are some different things we can look at. I'm going to give a couple examples here: high wrap mixes and preservation as two LCA questions we can answer. How much benefit do we going to high wrap mixes versus our current wrap recycled asphalt pavement use? And is preservation reduce our doing slurries and chip seals in between our overlays? Does that reduce our global warming, or is it better just let it fail and go do a rehab? So looking at rehab versus preservation, we looked at rehab with 2 preservations, and then a rehab. We looked at 1 preservation between rehabs, and we looked at rehab, no preservation. This is our functional unit. This is our analysis period. Our goal is to compare the global warming potential of these 3 alternatives. We're using 2-inch mill and overlays. We're using slurry seals for the preservation, make some other assumptions. Key to this is how long do our rehabs last without preservation? How long do our slurries extend the life of our rehabs? And here's some of our treatment impacts. A slurry has this many metric tons, and an overlay, the 2-inch overlay, has this many. So you can see preservation is quite a bit lower per treatment, but the question is, does it really extend the life, or are we just adding greenhouse gases and we're not getting enough extension of life to get the investment back? So a lot of numbers here. I'll let you look at these. The takeaway is that 2 preservations didn't look so good, because by the time we get to the 2nd preservation based on our pavement management system data, we're not getting so much extension of life. And so that actually was the 2nd highest. 1 preservation, we got bang for buck out of that. And just going to rehab, at least for our numbers and our performance, was the highest. So we did see a benefit of doing at least 1 preservation. And we saw some benefit of doing 2 preservations compared to just going to rehab. If you have no heavy traffic, you may not need to do a rehab if you do preservation in a timely manner. And if you don't have heavy traffic that's going to fatigue that rehab, you actually drop down to and just do a slurry every 6 years into perpetuity. We actually get down to 99 metric tons. So for residential streets, keeping on top of the preservation actually has a pretty big reduction, 50% reduction in global warming. High wrap versus conventional, there's the goal, there's the scope. We're looking at 40% wrap and the petroleum distillate recycling agent, and a lot of numbers. We also looked at whether we get the same life with the high wrap or if we don't get as good a life with the high wrap. And when we look at the results, if we're getting a 16-year life out of that 2-inch overlay, if we are getting the same life out of that, it gives us about an 8% reduction in global warming. Why is it not a 25% reduction? Well, part of it's because of that very carbon-intensive rejuvenating agent, and part of it is that we have to heat the aggregate hotter when we use the high wrap. If that wrap shortens the life by 3 years, we actually produce more global warming potential from using high wrap. And so this is why we have to answer all 3 of those questions: performance, cost, life cycle cost, and life cycle assessment. And recycling isn't always the better alternative if we're not getting same or better life. I want to mention environmental product declarations. These are now, these are basically like a cereal box of emissions from life cycle assessment for cradle to gate for a material. These are required in California. For some materials, they're going to be probably required for asphalt and concrete. We're collecting them through state specification right now. Buy Clean California Act. Colorado's just passed a federal act, and yesterday I got a text that the federal government has now just published a Buy Clean initiative. So if there's federal dollars involved, start expecting in the future to ask our industry to produce environmental product declarations. Where can we use LCA? We can use it in the planning stage when we include the social. We can use it in asset management. We can use it in conceptual and final design. And then we can use EPDs during procurement in construction, which is also LCA. So we expect all of these trends to continue, from the need for improved sustainability, the need to use science, data, and quantification to figure out set performance goals and see how we're doing, reduce the risk of unintended consequences. We want to start to incentivize this type of innovation, be less prescriptive, and set performance goals rather than do it this way, do it this way. We need continuous improvement. We need methods and tools to move ahead. And there's lots of places where we can do this. Last thing is, one other thing we're working on is how do we prioritize which strategies we should follow. And we've gone to something called the supply curve, or a marginal abatement curve. And what this is we use life cycle assessment to look at different strategies. Each of these boxes is a strategy, and we use life cycle assessment to see how far each strategy advances us towards our goal. But we also use life cycle cost analysis to figure out a bang for the buck metric. How much does it cost or does it save per ton of emissions reduced? And then we put these in rank order, and those that are less than 0, that means we reduce the environmental impact and we reduce life cycle cost. We should be doing these yesterday. And then we can prioritize so that with the dollars that we have, we can prioritize to get the maximum bang for the buck. And this has been applied to Caltrans. We've also looked at climate action plans by our local governments. This is an application that was done to some different strategies that Caltrans was considering, use of RAP, renewable energy production in the right-of-way, energy harvesting, optimizing pavement roughness, and so on. And this was our optimistic supply curve. We do a sensitivity analysis, and there's a different curve with the pessimistic assumptions. Last thing is we found that, or the state has found that, lo and behold, in the 20% of our neighborhoods that have the least pollution burden, those tend to be more advantaged neighborhoods and less people of color. And the 20% most polluted neighborhoods in the state tend to be overwhelmingly populated by people of color and poorer people. So our goal is to start to consider this and try to deal with some of this inequity. We're using a tool called CalEnviroscreen, which is at the neighborhood level, the census tract level. And this is Davis, pretty well off. This is some of the poorer neighborhoods in Sacramento. And we're looking at where do the emissions occur. At the federal level, and this is Tampa, and there's USF right there, and darker is less advantaged. There is a federal social vulnerability index, which can be used to map impacts as well. And these are some of the social impacts. I'm gonna wrap up here. I'm over time. I'll leave these for another time. So takeaways: method for applying LCA to pavement has been resolved. Guidance is available. LCA can be used in all phases. EPDs are moving forward. We want to use cost and environmental impact together, and social LCA is coming. And this is one of my heroes, S. David Freeman. He helped write, well, I'll let you read his biography. And he helped transform the energy sector in the 70s and 80s. The same thing, he got 4 feet from my face and said, listen, son, what are you going to tell your grandchildren? What have you done to help solve these problems? And if you say, well, I just did my job and I wasn't that concerned about it, he said, you know, are you going to be able to look your children and grandchildren in the face? The other thing is we're no longer a rich enough country to make a whole bunch of mistakes and miss it a couple times. We got to get it right, or pretty right, the first time. And I'll leave you with a YouTube of him there. And I would add, we got to focus our research and translate our results into practice and really communicate what we're doing and get feedback and criticism as we do it. Thank you. And sorry I went a little bit over there on the time.
Thank you, Dr. John Harvey, for your excellent presentation, and which contains a lot of information, and probably will take some time to digest after the talk. So now we can take a couple of questions from the audience. Let's see if anyone has any question or comments. If you are in the room, you can just take a mic and talk. And if you are online, then you can unmute yourself and talk.
I see some.
Could I ask a question?
Sure.
Yes, and thanks for your excellent presentation. And I noticed that some crack on the cement pavement near the transverse joint, and that was have a great impact on the draft, because they just have some and the small crack near the joint. Mm-hmm. And sometimes just the crack is very serious, and just but the crack is part of the lab. It's just some segment of that roadway, and just do how to just because I think and do have some effective rehabilitation method to replace just repair the crack.
Is that a jointed plain concrete pavement or a continuously reinforced concrete? It's got to be a jointed pavement if it's a corner crack.
Yeah, joint.
Yeah, the main method for that is, so as long as the crack has not affected the roughness, you'll probably leave it until it starts to affect the roughness. And then you're looking at a slab replacement. So taking that entire slab out, typically a local patch, sometimes a local patch will work, but often that local patch will sink some or impact the roughness, and it's often better to take the entire slab out. So slab replacement is typically the most effective treatment there.
Okay, thank you. And
Yeah, we also have questions from classroom. Do you have a mic? Yeah. Yeah. Can you hear the questions from classroom? Can you hear? Can you see something? Testing. Can you hear that?
Yeah.
Speak loudly. Yeah. I'm also a little deaf, so I'll turn the volume up.
Tried investing in sustainable pavements like traditional brick pavements. Yeah, for example, in Lakeland, we have restored several brick roads that were paved over without damaging the brick surface underneath. Also, when it comes to concrete surfaces, the concrete produced by the ancient Romans was completely carbon neutral and lasted much longer than concrete produced, through carbon-based methods. So.
I'm not sure if it was neutral, but it was often lower because I don't think it depended on how much they cooked it. We don't really know how much they cooked the limestone, but they also had some natural pozzolanic materials that as long as they mixed it with water, it actually increased the pH and got the cementation. That's actually a historical, I love history. That's a question that people have, is what actually was the Roman cement technology in detail? We know roughly what it is.
Other questions from?
So I guess I'll follow on to that question. What does that tell us about today? And a lot of that is, and that's the goal of the cement industry and the concrete industry, to get to net zero. They have a published plan. If you look at the Portland Cement Association and the California Nevada Cement Association, they have a net zero by 2050 plan. Involves using lower impact cements, such as Portland limestone, and also then replacing cement as much as possible with supplementary cementitious materials, and overall optimizing the aggregate gradation. And then some of the things they're also looking at are, if you take cement and break it up and expose it to air, it actually absorbs some of this, it carbonates, it absorbs some of the CO2 back out of the atmosphere. So it actually can be a sequester. The giant question is how much and how long, and that's the big research question. One of the biggest research questions for LCA in the cement and concrete world is, what kind of sequestration and what do we have to do to get it, and how long does it take in the end of life?
Mm-hmm. Okay, there's another question from the classroom.
Can you hear me?
Yeah.
All right. Thank you for the great presentation. A lot of valuable problem. My question is, do we know the effect of the rolling effect on pavement when we have in the future a lot of electric vehicles? So we know electric vehicles are way heavier. So are we going to have rolling effects? I don't know how much we know about that.
Well, that I cut that slide out because of time. I didn't cut enough slides out, but I cut that one out. So we recently did a study for the California State Legislature to look at that question. And we worked with our STEPS program at the Institute of Transportation Studies. And they looked at 4 different scenarios of how fast we're going to go to, this is about heavy vehicles. What are the different pathways to go to electric and then eventually to fuel cells? And fuel cells are actually eventually more viable for heavy trucks than electric. And as you mentioned, the battery driven trucks are quite a bit heavier. So then they had a technology pathway looking at how does the battery technology get better and reduce or increase the energy content of a pound of battery? And also, how fast is the transition to the lighter fuel cells? The fuel cells are actually lighter than internal combustion engines. When we map those pathways of transition to the vehicles and then map that on pavement performance, the pavement damaging effects were pretty negligible, because we're not going to make that transition tomorrow while the batteries are heavy. It's going to take about 30 years to implement that. And during that time, the anticipation is that those trucks will get lighter. So the net effect was a small impact. The least aggressive transition saved about 6 million metric tons per year out of 420. The most aggressive reduced it by about 35 million metric tons out of 420, which is really, really significant. So at least from the scenarios that we had and that 20-30 year transition, it looked like not much of an effect on the pavements, and a net very good gain. We also looked at natural gas as a bridge technology, and natural gas actually, because the tanks have to be heavier, because the fuel is under pressure, can increase the vehicle weight by 500 to 2,000 pounds. Natural gas actually, from pavement point of view, is a bit more damaging. And that report, if you Google Harvey Miller, Google some appropriate words, you'll find it, or I can send the link if people want it.
Okay, great. Any questions from online and from the classroom?
Hi, Dr. Harvey. Thank you so much for that fruitful information actually and presentation. So it has a lot of information. My question is regarding RAP, because according to the LCA, that using a high percentage of RAP, are like 40% RAP, in 16 years service life, it was better than 13 years with a quite a big difference. Can you explain a little bit how was that, maybe in your opinion, how that was concluded?
Yeah.
Also, and I would like to know what is the background, what's the kind of equation or the input you're putting to have such a quite our numbers like this. I mean, if I would like to increase the RAP percentage like for 80 or 100%, what kind of tools that I need to see to observe the whole effect of adding this RAP?
Sure. So there's two parts to it. The performance part, pavement performance part, we get from taking the mechanical properties, the stiffness, and the fatigue properties. We don't have that much of a rutting problem, but it's really about fatigue cracking for us. And we run those through our mechanistic empirical pavement design. So we would make the mix in the lab, test it, and then simulate it, and we might get a different answer. That was a 2-inch overlay. We might get a different answer if we put that in an 8-inch reconstruction. So again, everything is very, very context specific. Please don't take away that 40% RAP doesn't help us that much. It's very context specific. So you need to be able to predict the pavement performance using mechanistic empirical simulation, and then for the life cycle assessment, we take the materials and we get inventories for the processes. The other thing I want to point out in that example I did is I used, of our 3 rejuvenating agent possibilities, I used the most impactful one. So that was a very severe analysis. I used the petroleum distillate rejuvenating agent. If I used the tall oil, the pine tree based renewable rejuvenating agent, it has an impact, but it's less than the petroleum distillate. And we're finding in our current work on use of RAP that we can use about half of the tall oil rejuvenating agent compared to the petroleum distillate and get the same benefit. So if I reran that analysis with the tall oil, I'd probably get a much better number, a better number. So again, I want to emphasize that was a specific example. The key is getting the environmental flows for those, which you can then turn into impacts or get an EPD from the manufacturer. And with the EPD, they don't tell you what the flows are because that's proprietary, but they do the analysis and they have somebody from the outside review it and sign off on it, somebody who the market trusts. And then you just take the impacts and plug them into your numbers. So that's what we need to do, the environmental analysis. One issue we have right now is the rejuvenating agent and warm mix agent and concrete admixed industries are not producing much in the way of numbers. So we're having to go to their safety data sheets and look at the active ingredients and assume the worst. And that's what we've told them is until you produce real numbers, we're going to have to assume the worst and include those in our analysis. So in this case, I didn't have impacts from the petroleum distillate rejuvenating agent manufacturer. We looked at their safety data sheet and said, well, it looks like this, and we're going to use the worst assumption for it. So I do want to put those caveats on those numbers.
Thank you. Thank you so much.
Does that answer those questions?
Yes, sure. Yes.
Yeah.
Exactly. Thank you so much.
All right, great. I think due to the limited time, I guess there could be more questions. We will have to stop here. And John, thank you so much for this informative presentation. And I think we learned a lot from your talk. Thank you so much. Thank you so much. And for the next week, we invited Assistant Secretary of our FDOT, Mr. Brent Thorben, and he will talk about implementation of the IIJA, which is Infrastructure Investment and the Jobs Act. So we'll be same time and look forward to seeing you. All right, great. Thank you all for being here. And pizza is ready, drinks ready, and please enjoy. Thank you, John. Thank you so much.
Thank you. And
Thank you,
thanks.
John.
Yeah, I posted my email in the chat if people have follow-up questions. And it wasn't my strategy to go long so that I don't have questions. Just turned out that way. Thank you.
Thank you. And
Okay, bye-bye.
All right, bye.